Today, the goal is to practice some of the things that we learned in section 6.2 about transforming and combining random variables. All right. First, just for good measure, check. Can you guys hear me this morning? Just want to make sure. Hooray. Oh, that's good news. Thank you, Carly, for letting me know. Okay, excellent. Most excellent. All right. So now, what we're going to do today is do some practice with our newfound knowledge of section 6.2. All right, what's going on here? And do some examples. All right, we're going to do this using Desmos. We're going to do a little Desmos activity that I've created. And to do that, our first step, I'm going to put a link in the chat here. All right. What I need you to do is join the Desmos class that I've created for our class period. This will make it so that you have a place to go to find any activity that I create on Desmos that is for our classes. There's only one activity in there now, the one that we will be doing today. And so please click the link. Use your school email, please, because that will give the name that I have on record. If you use a personal email, sometimes the names don't show up to where I know who it is. And that's important. I need to know who it is. All right, so please use your school email. It makes things easier. I'm also going to share my screen right now to show if you would like to go a different route. You can go to student.desmos.com and type in the class code JVJMTR, and that will put you in the class as well. So you have a couple options there. So on our first page here, this is just a quick review of the concepts we covered yesterday in class about transforming and combining random variables. All right. Recall that adding or subtracting a constant a to a random variable increases or decreases the mean of the random variable by a, but does not affect its standard deviation or the shape of its probability distribution. Multiplying or dividing a random variable by a positive constant b multiplies or divides the mean of the random variable by b and the standard deviation by b, but does not change the shape of its probability distribution. Right, if you have a linear transformation of a random variable, meaning you are adding, subtracting a constant a and or multiplying or dividing by a constant b, then you can write the linear transformation of the random variable x in the form y equals a plus bx. So this is, in a nutshell, some of the things we did yesterday. So we're going to do some examples. All right, so now we're all going to move to the second slide. All right. So here we go. Our first example, a report of the National Center for Health and Statistics says that the height of a 20-year-old man chosen at random is a random variable h with mean 5.8 feet and standard deviation 0.24 feet. Find the mean and standard deviation of the height j of a randomly selected 20-year-old man in inches. There are 12 inches in a foot, just as a reminder. So we're doing a transformation to go from h to j by converting from feet to inches. And we're doing the standard deviation and the mean. So in the little answer box here, you can type in mean equals, type in your number, your deviation equals, type in your number, click submit and explain. The explain goes in this box. Do not try to write your explanation in with your numeric answer. It will type out really weird looking. Right, so please click the submit and explain to get the next section to explain. All right. So we're going to do this problem. I'm going to give you all just a couple minutes to do this one. If you have any questions along the way, please let me know. You can type them in the chat, unmute your mic and just shout at me or raise your hand. I'll be watching all the stuff. So it's been a couple minutes. Hopefully you've had a chance to attempt this problem. And so remember, we're going from feet to inches, so the unit of your solution should be in inches. All right. This is a transformation by multiplying. So that means the mean and standard deviation should both be multiplied by 12 because we're going from feet to inches. All right. 12 times 5.8 should give us a result of 69.6 inches, right? And then we should get a standard deviation of 2.88 inches by multiplying 0.24 by 12. All right. Is there any questions or anything I can clarify about this example? All right. Then we will move on to the next problem. The next problem is in 3 parts over the next 3 screens. So we'll be using the same context for the next 3 screens. All right. So Anna is a dedicated skee-ball player. See the photo below for what skee-ball is. Who always rolls for the 50-point slot. The probability distribution of Anna's score X on a single roll of the ball is shown below. You can check that the mean is 23.8 and the standard deviation is 12.63. Player receives 1 ticket from the game for every 10 points scored. We're going to make a graph, a histogram, of the probability distribution for the random variable t equals the number of tickets Anna gets on a randomly selected throw. And then describe its shape. I did not include an area to write the description, so just make sure you're thinking of how you could describe it. Now, to draw your histogram, the easiest thing to do is to, I believe, use this segment or line tool here. All right, and the number of tickets ranges from 1 to 5, right? Because 10 divided by 10 is 1, 20 divided by 10 is 2, and so on. Right? The 1 is going to be right around the middle of the histogram of between 0 and 2. Right? So we'll use the line tool, go up to 0.32, draw over and down, and we'll get something like that. That's, I think, the easiest way to draw the boxes. And so remember, this is a histogram. The boxes should be touching. All right. So where this box ends, the next box starts, and so on. Right. Once again, if you have any questions, please let me know. Otherwise, we're going to get started. Alrighty, hopefully you had an opportunity to draw your histogram. All right, so your histogram should look something like the one I have on my screen here. If you're looking at the shared screen, it should kind of look like a staircase going down from left to right, meaning it is skewed to the right. We have a peak at 1, right? Please make sure your histogram should not have started on the y-axis, right? Should have started slightly to the right of the y-axis. The y-axis represents a 0, which we do not have 0 represented as a possible score, right? Our center is probably going to be just to the right of 2, right? Because 50% of our data will be to the left of that, 50% to the right, or we can think of it as the mean, which would be the balance point, all right? And then there don't appear to be any outliers. So that's our basic description for our histogram here. All right. And many of you have a histogram that looks like it should, so that is fantastic news. That means we're going to move on to the next part of the question. All right, now remember, t can have possible values based on our provided table or probability distribution. Right? The possible values of t are 1, 2, 3, 4, or 5. All right? So we're going to skip it on over to the next part. All right, so this next part, using the same context and provided information, you're going to complete the probability distribution below for t, which is the table. So it should be describing the same probability distribution you just drew a histogram of, and you're going to find and interpret the mean of t. All right, so once again, you can type right into the table. Just click in and type in your numbers. That might look a little weird, but trust me, they'll be there. And then use a transformation to determine the mean of t. Type in your answer, right? Once again, hit submit and explain, and you can hit explain, which in this case should be interpreting what the mean of t is in context. I do not want you to explain how you calculated it. I want you to tell me what it means in this context. All right. Once again, if you do have questions, please let me know. Otherwise, I'm going to give you all a few minutes here on this one to do some work. Let's bring our attention back to me. So our probability distribution for t, the table, right? The probability should be the same exact set of probabilities that are from our score distribution, right? The probability of getting 1 ticket is the same probability as scoring 10, which means the probability of getting 1 ticket is 0.32, right? Probability of getting 2 tickets is the same as probability of getting 20 for a score, which means probability of 2 tickets is 0.27, right? And so on. The probabilities simply transfer over. They have not changed. Right? Is there any questions about that, about our probability distribution and the fact that the probabilities for this remain the same from our previous distribution? Right. And then, so the mean of t, right, the way that we're transforming x to t is we're dividing by 10, right? Because for every 10 points, we get a ticket, right? So dividing by 10, dividing the number of points by 10 gives us the number of tickets earned, right? So in this case, we will have the mu of t equals mu of x divided by 10, which then equals 2.38 tickets. Right? And in context, this means that we're playing over many rolls of skee ball, and I can expect to earn about 2.38 tickets per roll, give or take, right? This is our average. Right? Is there anything I can explain further about this example? Anything I can clarify?
Can you explain what x is? I'm getting lost.
Oh, are you looking at what I typed in here? Like mu of x?
Yeah.
So x is the original random variable we were provided in the context, right? That's Anna's score is represented by the random variable x for score on any given roll, right? So when we're talking about the mean, right, we use that notation mu, the Greek letter mu, and the subscript for mu is the random variable that it goes with, right? So in this case, we're finding and interpreting the expected value of t, or the mean of t. So we have mu of t equals, based on our notes and how we can calculate this, because it's dividing, we know that we divide the expected value of x by 10 in this case. So as notation goes, we say mu of x, so x is the subscript for our original mean, essentially, because that's our original random variable. Does that help?
Yeah, actually, never mind.
No, what's the question?
Oh, okay. Then what is, how do you get 2.38? Do you just...
So it's, here, let me do an extra step here. 23.8 divided by 10. Right, because 23.8 was the expected value for x, right? Sorry, I skipped the step, so I apologize. But yeah, so then, 23.8 divided by 10, we just move the decimal place one over to the left, and we get 2.38. Or we can punch in our calculator.
Okay, thanks.
You're welcome. Anything else I can clarify? So we're going to go to the last part of the skee ball question. There it is. So again, same exact concept, still dealing with the random variable x for the number for the score on any given roll, and t, number of tickets for a given roll, a randomly selected throw. We're now going to find and interpret the standard deviation of t, or sigma subscript t. All right. So once again, make sure you type in whatever numeric value you find for sigma. Hit submit and explain. Right, so let's say it's 1. Submit and explain, and please write what it means in this context in the explain box. If you try to type it in with a number, it just kind of types weird. Right? There you go. Can give you all just a couple minutes on this one. Remember, our transformation is dividing by 10. The only thing you need to decide is, does that transformation apply to the standard deviation? So bring your attention back over here. I know that some of you have finished, or at least gotten your solution, or you're working with it, or you're working to figure out how to type it in. That's fine. We're gonna review this real quick here. So the standard deviation of t, because we are multiplying or dividing, this transformation applies to the standard deviation. If we were adding or subtracting, it would not. The standard deviation would remain the same. In this case, we're dividing. This transformation applies. So to determine the standard deviation of t, take standard deviation of x and divide it by 10. That's going to be 12.63 divided by 10, which is 1.263. So I need an equal sign in there. That's better. All right. So again, in this case, because we are dividing, that type of transformation applies to the standard deviation as well. We divide by 10, we get our 1.263 tickets as the standard deviation from the mean. So that means, on average, on a randomly selected throw, the number of tickets Anna earns will vary from the mean of 2.38 by about 1.263 tickets. Right? Is there anything I can clarify or explain for you? And guys, do keep in mind, if I don't, in these types of solutions, I like that if you can show the work in here, like I have in my box here. However, if it's not cooperating, like, because it's kind of hard to get the notation to do what you want it to do sometimes, just type in the answer. That's totally fine as well. Okay. So just so you know. And you can also open up like a keyboard if you want more options on things. That's available. All right. So now, are there any questions about anything we've shown so far?
What does the OX stand for again?
Okay. So I'm going to mute your mic so I'm not getting feedback. If you need to say something, though, please unmute again. So this notation here, right, that looks kind of like a little O with the subscript T, or the O with the subscript X, right? It's also up here. That is actually the Greek letter sigma, the one that looks like a little O with like a tail on the top. That's the lowercase Greek letter sigma. It is typically used when talking about standard deviation because the first letter in standard deviation is S. And this is kind of the Greek letter that has the S sound. It'll be in other types of mathematics. You'll see sigma used in other things. If you take math courses in college and such, in our case in statistics, it has a significant meaning of talking about standard deviation. And so that's what that letter or that symbol means. The subscript attaches it to a random variable or a variable that it's referring to. So having the subscript of t with this sigma means that we're finding the standard deviation of t. When the x is attached to it, like it is here, that means that this is a standard deviation of x, of our random variable x. Okay, so it allows us to use a notation. So instead of writing out standard deviation of t, I can just do the symbols, and they mean the same thing. Right? You could also, it's somewhat common, just like we have the expected value and the mean are like interchangeable, where you can say e parentheses x. You could do SD parentheses x, and most people will understand what you're talking about. So there's that as well. Does that clarify what you needed clarified?
Yes.
All right. And the other thing to keep in mind, and it's not terribly important in high school, but it could become important in college, not all notation is unified within mathematics. So it's always good to clarify with your teacher or professor and the textbook on what they're using notations to mean. There's some things that are completely unified, like adding, subtracting, multiplying, dividing. Those symbols have special meanings. When you get into other types of math classes, they'll start just assigning meaning to symbols. So it's important to understand how that's being used for that class. So asking like, hey, what does this thing mean is a awesome question to ask. It's always good to clarify, right? Just to put that out there in the world. All right, so now the next thing we're going to do here is we have 3 other problems in this problem set. And so what I want to do is put you guys in breakout rooms. Let's see. How many people? I have 15 people here. So let's do, what do I have here? 4 rooms. Yeah, we'll do rooms of 3 or 4. So that should work. I'm losing people to the activities. That's a little odd. So what I'm going to do is we're going to go into breakout rooms. I'm going to give you guys 10 minutes. I know it will not be enough time to do all of the problems. But what I want you to do is look at the 3 different problems and amongst yourselves, talk about what you would need to do to solve them, what things you would need to understand, what would be the strategy, so to say. All right, so look at the 3 problems, make sure you understand the 3 problems, and come up with a way you could solve them. Solving them, if you have time, you could start on that, but it's only going to be 10 minutes. So the main idea is to make sense of and find a way to solve the problems. Then after the 10 minutes, we'll come back to the main room and I will answer any questions you have about the problems. So if you didn't understand something, if you want an explanation on how you could solve it, that will be the time for that. So now that we're back, what questions do you all have? What can I clarify? What can I explain?
How would you solve it? I didn't get a chance to finish it. I was still being confused on what I need to do.
Which one?
The making a profit.
Okay, I can show you. So let me share my screen. Excellent. Okay. So for this one, we're provided the mean and standard deviation of the random variable x, which is the amount of profit, right? Or wait, so the amount of profit x on random, yeah. All right, so that's our profit, random variable x. We have this distribution, all right? We know that the random variable y is defined by the linear transformation 0.9x minus 0.2. And this tells us how much money they actually retain because they have to pay a lender fee of $200,000 and 10% of the profits. So that's how we get 0.9, right? And the minus 0.2. Right? Finding the mean and standard deviation of y, right? The linear transformation, when we're multiplying and subtracting, applies, both of those things apply to the mean. So to get the mean of y, we take the mean of x, let's see, right? We go 0.9 times the mean of x minus 0.2, and that will be 0.9 times 3, right, minus 0.2. Right, and that ultimately gets us to, what is it, 2.5, right, in millions of dollars, 2.5 million, right? So in this case, it's for the mean, we're just simply putting the mean into the linear transformation. Right, for the next one, for the standard deviation, we need to remember that standard deviation is only affected by multiplying or dividing, not adding or subtracting. So when it comes to the standard deviation is just going to be 0.9 times our standard deviation of x, which will be 0.9 times 2.52. And that will give us, what is it, 2.268. If you got 2.068, that means you subtracted the 0.2 when you didn't have to, right? So for this problem, right, we could do these calculations if we wanted to. It would take more time, it would take more effort. We don't want to do that if we don't have to. So we used what we know about linear transformations. The entire linear transformation applies to the mean, but only the multiplying applies to the standard deviation. Right. Does that answer your question, Nathan?
Yeah.
Sweetie. All right. All right. So then our rainy day problem, this is about understanding the concept. In this case, for the first part, yes, it is reasonable to take the mean of total rainfall to be the mean of x plus the mean of y, right? This is because when adding means, it's always okay to add the means of two random variables if you're combining those two random variables. It does not matter if those random variables are independent or not. All right, so whatever else is going on, if I want to add and combine two random variables, I can, and to find the mean, I add their means. When it comes to variance, right, the only time I'm allowed to add variance is if the events, the two random variables, are independent. In this case, it is not reasonable to add the variances because these events are not independent, right? X and Y are not independent random variables. And that's because if I know the amount of rainfall in Orlando outside the airport, right, if I know what happened there, I know that it's raining, it changes the likelihood of it raining at Disney World. Right? Those two things influence and affect each other. So they're not independent. So we cannot add the variances. Is there anything else I can explain about this one? Lastly, we have two situations going on here, right? We have the time required to bring a part from a bin to its position on the chassis, and the amount of time it takes to attach the part to the chassis. Right? These are two, we're being told, independent events. Knowing how much time it took for one thing does not affect the amount of time it takes for the other thing. We're considering those independent. And both of these random variables are normally distributed. Right, one has the first part going bend to chassis is 11 seconds for the mean and 2 for the standard deviation. And attaching the part has a mean of 20 seconds and a standard deviation of 4 seconds. All right. So whenever you combine two normally distributed random variables, then, or independent and all this stuff, the result is also a normal distribution. All right. The mean will be the sum of the means. So 11 plus 20, we get 31 seconds. And the standard deviation, right, will be we need to first convert these two variances, add the variances, take the square root. Right, we get 2 squared plus 4 squared. That gives us 20. Square root of 20 is, I believe it was like 4.47 from what I did yesterday. Yeah, sweet. All right, so we get a normally distributed new random variable that's a combination of these two things with a mean of 31 and a standard deviation of 4.47. Then we have to use table A and standardizing our scores, our score of 30, right, to then determine what the probability that this process takes less than 30 seconds. Right? When we standardize 30, we get 30 minus 31 divided by 4.47. Give me notes. And that gives us a negative 0.22. When we go find negative 0.22 on table A, negative 0.22, we get 0.4129. Yep. Right, and that is the proportion under the curve to the left of that z-score, right? That's our probability to the left. So that means the probability of x being less than or equal to 30 seconds is equal to the probability of z being less than or equal to negative 0.22, which is 0.4129. Right, and so that means that there's about a 41% chance that this process takes less than 30 seconds on any randomly selected part that they're tracking. Right. Is there any other questions? All right. So then that is our activity for today. You'll have access to this Desmos activity if you'd like to revisit it. It'll be linked in the Canvas course. Other than that, we are done for today. You guys should enjoy your weekend. Have a great rest of your day, and I will see you next Thursday for the regularly scheduled class. All right. And if you do have any questions along the way while we're out of class, please email me, let me know, and I will be happy to help.